Bismillahirrahmanirrahim. Today our topic of discussion is electronic configuration of elements. Outline of the present session will include its introduction, and there are three rules which will be discussed over here to arrange the electrons around the nucleus. These are Pauli exclusion, Horn's rule, and Aufbau principle. And then we will be able to write the electronic configuration of the periodic table of some elements from periods 1 to 3 and 4 to 7, especially with respect to normal elements, S and P block elements. And then I will summarize this session. At the end, you will be able to write the electronic configuration of the periodic table. So you will be able to write the electronic configuration of any elements in the periodic table if you know the atomic number of that element. First of all, introduction to this topic. You know that the elements are an atom has electrons around its nucleus. And you know that this electronic configuration means that how how these electrons are distributed around the nucleus, and this distribution is based on different principles we will discuss in this session, that how the electrons are arranged around the nucleus. This arrangement of electrons around the nucleus is called electronic configuration. For this purpose, you should note that what is the basic model of an atom and what is atomic mass, that is equal to neutron plus proton, and what is the atomic number. Atomic number is the number of electrons or number of protons in an atom. So we will write the electronic configuration on the basis of atomic number. Why? Because these represents the number of electrons. And you know that in a model of atom, the nucleus has protons and neutrons, and the electrons which are revolving around this nucleus in certain path known as orbit. This is known as orbit, or in the other word is shell. And the shell is the orbital. You can say that each shell is further divided into subshell, which are known as orbital. So what is orbital? Orbital is nothing. It is just you can say you can find the probability of finding electron maximum in an orbital. So it is not a hard surface area. You can say that if the probability of electron is high, then this is the orbital. So there are different types of orbital. First of all, in one first shell there is s orbital. In second shell there are s and p shell, subshell, and in m there are s, p, and d, where n shell is further divided into s, p, d, f. What is s? This is the shape of s orbital. However, the p orbital is dumbbell shape, and you can write over here in this way. These are px, py, and pz, three p orbitals, and here are d orbital. There are 1, 2, 3, 4, and 5. Five types of d orbitals. For example, dz square, dxz, dx square minus y square, dxy, and dyz. So these are five types of d orbital. So you can say that there is only one type of s orbital and one type of s and three type of p orbital in the L shell, whereas in M shell there are one s, three p, and five d orbital. In N shell, there is an addition of F orbital, which is further complicated. You can see the um, shapes of orbitals. This, this is further clear picture for the d orbitals. Now f orbital, there are 7 f orbitals. On the basis of their shape, you can say that these are 7f orbital. Each is represented with its name according to its orientation in 3D space. First of all, Pauli exclusion principle. Pauli exclusion principle states that no two electrons in the same atom can have identical values for all four of their quantum numbers. It means कि जितने भी ऑर्बिटल में दो इलेक्ट्रॉन्स जो हैं उन दोनों के क्वांटम नंबर सेट ऑफ क्वांटम नंबर्स में डिफरेंस होगा यानी 3 quantum numbers will be same और एक जो है at least one quantum number should be different for both so that they can be placed in an orbital. So here is an example. You can say that if we have 1s and 2s, you can write it in this way because the spin is opposite. If you can write it in this way, the spin is parallel. It means that they have the same spin quantum number along with the other 3 quantum numbers. So it is not written in this way. So Pauli exclusion principle states that both electrons in an orbital have the different spin quantum number are different set of four values. So you can place the two electrons in an orbital. That is the conclusion. You can in an orbital you can place maximum two orbitals and two electrons. So the two electron must have different set of values of quantum number. It means they should have opposite spin like this as compared to the parallel spin. The second rule is very important, that is Hund's rule. It says that electrons always enter to an empty orbital if it is available, if there is a degenerate set of orbital. What is meant by degenerate? It means the orbital with the same energy and same shape. If you say the carbon, that two electrons are in the 1s orbital, two in the 2s orbital, and however, if you say the sixth atomic number, it means the two electrons are still there. But these two electrons find empty space for the three 2p orbitals. 2px, 2py, and 2pz. That is why the sixth electron will try to accommodate over here rather than to accommodate over here, and um, it will be easy for that electron to accommodate in an empty orbital. That is a rule which is described by Hund's and known as Hund's rule. Similarly, for nitrogen, the seventh orbital also will fill this free accommodation, will be accommodated over here. So you can say that these electrons will prefer to accommodate it in this way. However, it has vacancy over here too. So every orbital in a sublevel is singly occupied in is another statement. So these are singly occupied. And you can also say that the orbitals in the same spin, all of the electrons in singly occupied orbitals have the same spins. So you can say Hund's rule of multiple maximum multiplicity, which shows that the electrons in an atom in an element has maximum spin multiplicity, and this can also only be achieved if the electrons are accommodated in empty orbitals singly occupied. Further, Hund's rule can be applied to, for example, this one 1s2, 2s2 for helium, for lithium, this is electronic configuration. This is for boron, sorry, this is for boron, and this is for carbon, nitrogen, here is oxygen, fluorine, and then neon. Aufbau principle is a third principle which shows that how the orbitals are arranged in order of their increasing energy level. So this is the way these orbitals are written in this way. For example, K shell has only one s orbital, L has two s and two p, M 3s, 3p and 3d, N 4s, 4p and 4d and 4f, O, P, Q. So you can write it in this way. 1s, so first come 1s, then 2s, and then 2p, 3s, 3p, and before writing 3d, so you will write over here 4s because 4s the lower energy as compared to 3d. And then after writing 3d, you will write 4p and then 5s. So this is the sequence. So here is 1s, 2s, 2p, 3s, 3p, 4s, and then 3d, and then 4p. So this is the according to the Aufbau principle. So in case of period number 1, you will see the first element is hydrogen. The electronic configuration is very simple, that is 1s1. Similarly, for helium, you will see it is 1s2. If the two electrons are there in an orbital, you will see that they have different set of values of quantum number. So each the three quantum numbers are same, whereas the fourth one is different. For one electron, it is plus half, and for another electron, it is minus half. So the helium electronic configuration can also be written as 1s2. So if you are going to write the electronic configuration for lithium, whose atomic number is 3, so you can write over here 1s2 and 2s1. This can also be written in this way. For beryllium, for boron, 2p1. For carbon, it is 1s2, 2s2, 2p2. So these two electrons are expressed in this way in order to follow the Hund's rule. And rest of the electronic configuration you can see over here. For nitrogen, that is 2s2, 2p3, oxygen 2s2, 2p4, fluorine 2s2, 2p5, and for neon it is 2s2, 2p6. From sodium to argon, you can see the electronic configuration in this way. For sodium, it is and valence electronic configuration is 3s1, and for argon, it is 3p6, 3s2, 3p6. You can also write another notation for, you can use another notation for electronic configuration, that is noble bond, noble gas notation. So the inner shell electronic configuration is represented by the noble gas, the noble gas enclosed in these brackets. You can say that the chlorine, whose electronic configuration, inner shell electronic configuration is similar to neon, so it can be written over here neon, and then 3s2 and 3p5. This is the valence shell electronic configuration, and this is inner shell electronic configuration, which is represented by noble gas. In case of transition elements, scandium, which is the first one element, and the first 3d orbital will come in this one, and then you will write over here various electronic configuration for transition elements like titanium, vanadium, chromium. Each is represented over here. This is noble gas notation. Argon, inner shell is just like argon. For potassium, which is not transition element, alkali earth metals. So this is the electronic configuration of titanium. Here is vanadium and here is chromium. You can see that electronic configuration of chromium is 4s1 and 3d5. This is due to the fact that
The electron in the 4s orbital will prefer to accommodate over here in order to follow Hund's rule of maximum multiplicity. This is also due to the fact that this 4s electron has 4s orbital has same energy, more or less same energy as 3d. So the electron will prefer to attain over here in order to get more stable ground state. So you can say the electronic configuration of rest of the transition element in this series, 3D series, is manganese, here 4s2, 3d5, iron, cobalt, copper, nickel, zinc, and selenium. Sorry, it is scandium, Sc scandium. So on the basis of valence electronic configuration, so you can write over here, this is 1s, alkali metals. Sorry, it is these are alkali metals. Here are alkaline earth metals, 2s, 3s, 4s. So this is S block. On the basis of valence electronic configuration, this is D block, and it is P block, and then it is F block element, lanthanides and actinides. So this was about the electronic configuration of the elements. I hope you can write electronic configuration of any element from the periodic table.